Perfecto. Doctor Iram, ¿está por ahí? Ok, perfecto. Bueno, pues un minutito a ver si se conecta el doctor Iram. Ok, bueno, vamos a esperar un minuto más y comenzamos con la charla. Perfecto. Bueno, buenas tardes a todos. Es un gusto para mí dar inicio a esta semana, que es el Fall Fest de Qiskit. Esta semana de talleres y el hackathon, que ha sido organizada por el CIC-IPN con apoyo de IBM, y un especial agradecimiento a todos los que han hecho esto posible, incluyendo el director Francisco Ram y a Alberto Maldonado, que se ha encargado de hacer toda la coordinación. Y perfecto, bueno, antes de empezar, les quiero comentar, el primer taller va a ser el de introducción a la cómputo cuántico por Lia Yeh, de la Universidad de Oxford. Pues, Lia, when you want to start, it's ready.
Tuve un problema con su conexión a internet. Ahorita regresa.
Ok, perfecto. Bueno, en lo que se
Igual la
conecta.
puedes agregar como co-host para cuando regrese, para que tenga acceso a toda la herramienta y poder hacerla, a compartir pantalla y demás.
Perfecto, sí, ya la haré como host. Ah, perfecto. Bueno, en lo que se resuelve el problema técnico, Alberto, ¿nos podrías comentar un poco de qué va a tratar este Fall Fest para las personas que asisten por primera vez a este evento?
Bueno, yo soy parte de la desorganización, creo, de este evento. Bueno, el motivo de esto es que es por parte de diferentes comunidades o universidades. Estamos realizando al mismo tiempo en este mes de octubre un hackathon o una semana de talleres o retos o una escuela. En esta ocasión nosotros estamos haciendo un hackathon y un tipo bootcamp donde van a abordar diferentes áreas de la computación cuántica, ya sea hardware, software, algoritmos cuánticos, quantum machine learning, introducción a esta misma, Calculus, todas las aplicaciones que actualmente se tienen en la computación cuántica por parte de expertos, tanto sea en la parte de la academia como en la industria, ya que tuvimos un apoyo por parte de diferentes empresas como lo que es Xanadu, Unitary Info, Multiverse Computing, Tropical Labs, Qubit, entre otras, donde nos van a apoyar con su área de experiencia y sus grandes conocimientos para que nosotros podamos resolver ya sea aplicaciones de computación cuántica y en la siguiente semana vamos a tener diferentes retos por parte de Xanadu, Anthropic Labs, Quantum Universal Education, Covalent y lo que es la parte de Qiskit, que es un proyecto abierto que ustedes necesitan solamente saber Qiskit o emplear un concepto de computación cuántica. Entonces, estos talleres les van a ayudar para dos partes, para que ustedes logren saber un poquito de computación cuántica de manera introductoria y que logren generar un proyecto. Ese proyecto va a ser libre. ¿Qué quiere decir con esto? Que es código abierto. Nosotros lo que les vamos a dar son las herramientas para que ustedes logren eso. Va a ser su reconocimiento de ustedes. Se va a difundir ese proyecto en nuestras redes sociales, en nuestra plataforma y validado por lo que son IBM y nuestros sponsors, en estos casos dependiendo del taller y el reto en el que quieran participar. También, aunado a esto, lo que queremos es que ustedes se motiven a introducirse mucho en esta parte. De hecho, en este día, a las 4 p.m. vamos a tener una plática por parte de Unitary Fund, quienes nos van a hablar de cómo tener un financiamiento, un microgrant de $4,000 para un proyecto ya sea de investigación, un software que tenga relación con computación cuántica. Aquí la idea, lo que ellos tienen y lo que nosotros queremos explorar en esta área es que en Latinoamérica podamos iniciar en lo que es la computación cuántica y también lo que nosotros nos podamos improvisar, mejorar en este aspecto. Y no necesariamente en Latinoamérica, sino en otra parte del mundo. Igual vamos a tener gente experta que nos va a dar talleres o foros, más bien en este caso, sobre cómo es la computación cuántica, cómo iniciar en lo que es el código abierto y los retos que se pueden dar. Igual en los premios de cada categoría se les van a dar por parte de la empresa y eso validado como reconocimiento para ustedes. Entonces igual les invitamos a que ustedes se inicien en esta área, participen con su proyecto, no necesariamente hacer algo increíble como ustedes que van a ver en los talleres, aunque lo curioso es esto. Cualquier cosa que hagan cuánticamente para mí ya es algo increíble porque es un tema muy complicado, algo muy difícil de hacer. Entonces serían 5 días que ustedes tendrán para lograr algo que ustedes aprendieron en esta semana de talleres y se les van a dar los recursos también que se den en estos talleres para que ustedes sigan en esta área y si quieren meterse a algo más profesional, adelante. Esa es la idea de estos tipos de eventos. Muchas gracias, José Ángel.
Muchas gracias, Alberto.
Lia, are you there?
Yes, I'm ready.
Perfecto.
Okay. If you want, can you share your screen, Lia?
Perfect, yeah. When you're ready, you can start.
Leah, are you there? I think your microphone is mute.
Hello, everyone. Welcome to the quantum computing intro to quantum computing workshop of the Qiskit Fall Fest 2022 IPN Mexico Hackathon. I'm a PhD student in the computer science department at the University of Oxford, and Alberto, who also prepared this presentation with me, is a computer science PhD student in the Centro de Investigación en Computación in Mexico, where this hackathon is based out of. A very big welcome to everyone. So this is a workshop as a Qiskit Fall Fest hackathon. This is part of a bunch of hackathons happening and supported by IBM Quantum Education, where I worked part-time in the past year. And so we're here to answer questions if you have any about using Qiskit and many other quantum computing software and hardware as well. I hope you all learn a lot from this hackathon and the week of workshops that we prepared for them. First, I'll start off by Alberto and I are both part of an organization called Quantum Universal Education. We have a Discord server. Here we're sponsoring a best education hack for this hackathon prize, and we develop open source, open access, free quantum educational learning materials. It's a blog which anyone can contribute, and we give out free t-shirts thanks to the nonprofit Unitary Fund. So you can join our Discord. You can also, we do many events, including the first quantum education conference recently. This was the workshop that was a year before that. To get started into, first I'll give an overall introduction to quantum computing, and then I'll dive into some more specifics. So we will have a little bit technical part where we cover the definitions of qubits in terms of the just basic linear algebra, so matrices and vectors, and then beyond that, you'll get to play with the software by the end of the workshop. Give me a sec. Let me update my screen a bit. Okay. So this is a plot from 2019. This was a paper that gave an overview of the what we can expect, what region of quantum computation we're in today, and how that compares against classical computers, and what we can expect in the coming years. So on the bottom axis, this horizontal axis is gate error probability. So the biggest obstacle to quantum computers becoming more relevant and usable and practical, ready to tackle real world problems that we have today could range from carbon capture to finding new fertilizers to optimization of supply chain or finance. There's many different optimization and algorithms that people believe quantum computers can have. We have strong reason to believe that quantum computers would be better suited for than classical computers. So our quantum computers today fall in this green bottom left region. So in the vertical axis is our number of qubits. This was actually in 2019. So we're actually at about the hundreds of 1,000 qubit range right now, depending on your hardware. So, and this blue dash line is the classical simulation. So this represents this boundary of how much we can achieve with classical simulation. And as you get farther to the up and right, you get more advanced and more capable computation. So this, I think the estimates for how far these regimes are has kind of halved in distance, has halved, but this is log scales, but has gotten a lot closer because we're getting better at how to compile our systems, and our hardware is getting better. But this red region is to run some Heisenberg algorithm. This green dash region is to run Shor's on fault-tolerant quantum computers, and this yellow is for Yeah. So basically, these regions are for different algorithms. And so you can see there's quite a bit of distance we'll need to cover in order to get quantum computers from where they are today to where it needs to be for us to do to be able to tackle these foreseeable long-term applications in a fault-tolerant quantum computer when we are able to correct errors on quantum computers faster than they are produced. And so this is probably a problem some of you will tackle at this hackathon or in the future. This is a really important problem of not only the hardware to get our hardware to have less errors, but also to get the theory and software in order to correct these errors and to mitigate these errors as they occur. And so this is from 2018. People started to sketch out, okay, so when classical computers were invented for the first time, actually people, they couldn't do that much and had really little memory, and people mostly thought of it as a way to play games. And so at that time, you had these algorithms that people had thought of in a few centuries ago of some math that you could run on some computers if we had it powerful enough. But then in practice, we just have these really simple circuits and basically are programming in zeros and ones and punch cards. So today, this is a very simplified view, but there's many different layers and modules that can go into a classical computer. And but meanwhile, if we can see that quantum computers, how they are presently, we're still figuring out everything that goes in between. So there's many different proposals for how to bridge these algorithms and these the hardware that we have. This is here is just an overview. This is not comprehensive, but it shows quite a few different attempts at making. These are different approaches to making quantum hardware. So these, most of these are qubits, but basically you will be able to, because, well, as we'll later see next in this presentation, a qubit is a logical. It's basically a quantum bit. It's something logical, but how you implement it on hardware, many different physical systems can do that. So, so we'll see, for example, IBM, Google, Rigetti, and are working on Oxford quantum circuits are working on superconducting quantum computers. IonQ and Quantinuum are working on trapped ion quantum computers. Xanadu is working on, and yeah, they're working on photonic quantum computers, and then you'll see a lot of different hardwares but that you can do the same. You can run the same software on. You can run them, but how the hardware is implemented could be some different gates than the actual software that you have. To show an idea of what we're talking about, what we can expect in the coming years. So many companies have projections, which make hardware, have these projections for how much they expect their quantum computers to be capable of. So one simple way to describe it with one number is just the number of qubits, but that's actually not too accurate because it also depends on how good your quality of qubits are. And so a better people are still working on different ways to measure this, but one way to indicate this could be on what it's capable of. So what kind of applications and algorithms you can run on it. This is the development roadmap for IBM Quantum, so that they released publicly earlier this year in 2022. So you can see, although right now we're in 2022, we already saw that they released 100-something qubits. We're going up. But we're in the 100 to 1,000 range of qubits right now. But we're going to within the decade, we're going to expect to be able to see some quantum software applications. So one thing you'll notice is that the amount of computational power is expected to increase exponentially over time. And this is the quantum equivalent of Moore's law in classical computing. And this is also from before, but it's previously, this is, I think, a few years ago, it was 2020, it was possible to keep a lot of the companies that were involved in quantum on a single slide. Nowadays, even just within a single country, the amount of companies and institutes and collaborations that are involved in quantum is just so much that now it's more like we need one of these slides for each of the most involved countries in quantum. So now there's hundreds of companies that are involved in quantum. There's a lot of interest because it's a new type of computer that will be able to do computation that we think our current types of computer won't be able to handle. So this wraps up the kind of overview part of this workshop. And next I can go over, we'll start with the basics. So Alberto has drawn these really, really good images. He also has a whole series of comics. So definitely ask him about it. It's also posted on our social media of Quantum Universal Education. So on the left, this basically is a classical bit. So all information on your computers is encoded as these bits. So it has either value 0 or 1. And you can just think of this as some voltage along a wire, and if that voltage is above or below, if there's a certain threshold. But a quantum bit is a lot more involved because quantum bit isn't restricted to just being either 0 or 1, but it can actually be a superposition. And what the word superposition means in quantum information is that it could be both 0. It could have a different probability of being 0 or 1. And so if you had a classical coin, it's going to be either heads or tails. But a quantum coin, you could have it be in a state where it is, you're not sure if it is 0 or 1, and but there are some rules that these probabilities must satisfy. And so quantum mechanics is arguably the most successful theory in the history of physics in the past century. So what a qubit is just if you take information theory and computer science and apply it to quantum mechanics. In the top left, you have Qiskit. This is a generic 1 qubit state, and it's equal to any 1 qubit state can be written in this form mathematically. Here, Ket 0 and Ket 1, what they are is down here on the left where my cursor is. Ket 0 is equal to 2-element vector. It's just with a 1, it's a vector with 1 here on top and 0 on the bottom. Meanwhile, Ket 1 is this on the right-hand side, 2-element vector with a 0 on the top and the 1 on the bottom. So this is just a different notation that introduced by the physicist Paul Dirac for these vectors. And it turns out it's just a little bit convenient, but it's just a different notation. And this alpha and beta, back to this top left here, this alpha and beta are complex numbers. So complex numbers can be written in the form, so a plus bi for real numbers a and b, where I is the imaginary number. But for our purposes, you don't have to worry about the complex numbers here. So basically, if you take the norm squared, if you add up these complex numbers, alpha and beta, you always get 1. And this basically means that our probabilities are conserved. So what we can see in real life, which is real numbers, those things, and the probabilities of that will all be as we expect. If you have multiple qubits, then you have a tensor product. So Alberto has this great comic on tensor product, but basically how we notate that in bracket notation is that, and what it works out to is that you can, instead of having Ket 0, you can have Ket 0, 0, and this is this bit string here. So it just means that you have different qubits side by side, but you can have them be entangled. So that's something we're going to get to in the coming slides basically we're going to, in the next few slides, build up to what it means to entangle different qubits together. Basically, this sentence right here entanglement would be that it's impossible to represent a state of two qubits, qubit 1 and qubit 2, as the state of qubit 1 next to the state of qubit 2. So if they're entangled, then they're interdependent on each other, and you can't separate them like this. Lastly, focus on this thing in the center. So you may recognize this as a sphere or something kind of like a globe. The reason why it's like a globe is so this is 3D. So we can think of this x-axis. So this x here is this horizontal part. If you imagine a horizontal part through here, then at the plus x-axis, you have this ket plus state, and then at the negative x-axis side, you have the ket minus state. And whereas on the z-axis, so this vertical one, at the plus z side, you have ket 0, and at the minus z side, you have ket 1. So this is a sphere on which you can plot any single qubit state. So any single qubit state you can plot on the surface of the sphere if it's a pure state, and if it's a mixed state, so a mixture of the states on the surface of the sphere, then it can plot it inside the volume of the sphere. And something that's super interesting is that because you're drawing them on a sphere, you can visualize any operation on a single qubit as just a rotation operation on the sphere, like just rotating at all your points on the sphere. So earlier I mentioned superposition. The most important states, or commonly used states for superposition, is that here on the right hand side, this ket plus state is the equal superposition of ket 0 and ket 1. So this is equal because if you measure this ket plus in the ket 0 spaces, you'll get ket 0 half the, if you measure ket plus in the z-axis spaces, so the z basis, then you'll get ket 0 half the time and 1 half the time. And notice how then on this alpha is 1 over square root of 2 here in the top left equation, and then beta is 1 over square root of 2 also. So this purple equation where my cursor is here, this just becomes half plus half is equal to 1. So your probability of all the possible outcomes that you could observe is equal to 1. So I've been talking a lot about probabilities, but we can also now talk about gates as well. So we talked about qubit state so far. This U in the top left, this stands for U for unitary. So any gates on a quantum computer that we would want to implement efficiently, we would want it to be unitary. So this means that we're able to reverse it. If you this unitary basically if this is your block sphere, but now we're drawing it 2D just to make it simpler. So your unitary could change, is something that, as I said before, rotates this block sphere. So rotates the points on the block sphere. And this top, although I wouldn't say it's exactly it's not an equal sign, but in n qubits, you will store 2 to the n bits of, 2 to the n values. These are 2 to the n complex numbers that you're storing in the state of any state of n qubits that are entangled qubits. However, it's not I would say it's not exactly an equal sign because but this is it's pretty subtle, is that you can't observe all of these 2 to the n values. You do have to so you can store that much, but to actually you can only observe some of them at a time. But this is a unique property of quantum information. So any quantum circuit, as we'll see in the coming slides, is going to just, in the simplest way, is just to see that the left side, it's going to be read from left to right. And the left side, you'll have your inputs, and on the right side, you'll have outputs, and then in the middle is the actual quantum circuit, which we hope is unitary. And unitary satisfies this equation that it's reversible, so there's always exists this other operation that's called U with a dagger in the top right, so we call it U dagger. It's basically taking the complex conjugate transpose of the matrix of U, but so there's always exists another operation that's related to U, such that if you apply it after you apply U, then it's equal to I, the identity matrix, which is the same as doing nothing. One thing I'll note is that when you write matrices, because you multiply matrices from right to left, you read these matrices from right to left. So first you do U, and then you do U dagger here. But however, for quantum circuits, you'll notice the convention is go from left to right, as if we're reading in English, or most languages, you read from left to right in most languages. So that's just one thing to note that can commonly confuse people. It's just a coincidence of the conventions. So as mentioned previously, the bottom left of the probability to obtain any state is equal to norm of alpha squared, where alpha is the complex number. And measurement is something we'll also see on the coming slides. And any unitary is this U is just, we're just using a notation, so we're not writing out the whole matrix anytime, but U is a matrix. Here we just drew the identity matrix, but it's any unitary matrix. So unitary just means any reversible matrix, reversible complex value matrix, a square matrix here. So now we can get to having some concrete gates. First, I'll cover some single qubit gates. This is the most important one. So now, just for fun, we're drawing a happy cat as the ket 0 state, and a not happy cat as the ket 1 state. Or I said happy and sad, but I guess how they're drawn here is actually alive and dead, like Schrodinger's, as we'll see. As we'll see in I think the next slide. So this is the happy cat. If you apply an X gate to it, it becomes unhappy. So this X gate is the bit flip gate, also called poly X. And this takes any bit and flips it. So it takes ket 0 to ket 1 and ket 1 to ket 0. So it makes this a happy cat sad and a sad cat happy. So how we write it as a circuit is this top half of this slide. On the left-hand side is this ket 0. And then in the middle, this is just a box with an X on it. And then this is just a notation because we know what the X gate is. And on the right-hand side, this is the output state. You don't have to necessarily write the output state, and sometimes you don't know that. That's what the quantum circuit is computing. But in this case, we can compute it easily by just multiplying the matrices. So on the left, this matrix is this one right here, because for matrices you read right to left. So this is the ket 0 state. Its vector, the state vector for it, and this is the vector. This is the matrix for the X gate, and this is the matrix you get when you multiply the two. So although you can, in theory, do all quantum computing circuits, you could compute it via matrix multiplication, but then that's just classical computing, and that's not efficient. So that's the whole point of quantum computing, is that it's really expensive to multiply all these matrices classically. But if we can run them on quantum computers, we just have the quantum computer do the computation, but we don't actually know what the output matrix is. We can observe many things about it. Here is another important gate. This is a single qubit gate, and remember earlier I talked about the ket 0 and 1 states are on either end of the z-axis of the Bloch sphere, and the ket plus and ket minus states are on either end of the x-axis. So this H gate is what changes between these two axes. So it sends ket 0 to ket plus to ket 0, and it sends ket 1 to ket minus, and ket minus to ket 0. So sorry, ket minus to ket 1. So here on the left-hand side, this is ket 0. And then here we're applying this. This is the matrix of the H gate. And then what you get is this right-hand side, you get this is ket plus. This is the equal superposition. So the norm of this number and norm of this number is the same. So this is equal superposition of ket 0 and ket 1. So something I'll notice is, I'll just say here is that the reason why we drew cats is because historically Schrodinger's cat is that thing that you have a cat inside a box and either the cat is half alive or half, the cat is either alive or dead, or you don't know if the cat is alive or dead, basically. You don't know the state of the cat's mortality. So you can, the only way to know is to really, even if you just shake the box, you don't know if the cat is, it's just some robot inside that makes a cat sound, meow, when you shake the box. So let's say you have to observe the cat to know if the cat is alive or dead. And so while the cat is inside the box, the kind of toy, this scenario is that the cat is somehow both or equally alive and not dead, because without seeing it, you can't know which one of it is. And so the state of the cat is not determined. So that's why we drew cats. So here, this is now talking a bit about measurement. So it said before, measurement is that whenever you have this is a quantum state, the coefficient of, if you write out a quantum state in terms of orthonormal basis, so this just means that you cannot have a cat actually be both alive and dead, then here, this coefficient, if you square it, you get the probability. For if this was a complex number, you would take the norm squared instead of the square, but this is a real number. So square root of 1/3 squared is 1/3. And if you take this thing, the square root of 2/3, and you square that, you get 2/3. And this means that your probability of the cat, if you have a cat in this specific state, and then you observe it, then you'll see it has a 1/3 probability of being alive and a 2/3 of being dead. I mentioned before that if you have multiple qubits, then you could take a tensor product of their states if those are not entangled. So it just means this, you can think of this tensor product as just being side by side. And that's what you're doing whenever you draw any quantum circuit or other diagrams of your quantum computation. If you draw it side by side, that you're secretly doing this tensor product operation mathematically. At least for most quantum circuits. So so this is just some of the math. But Alberto can send around the really helpful comic that he made with the cute cat drawings about what is the tensor product. And lastly, for the gates part of this talk. So here, we finally get to 2 qubit states and gates. And so we see the Hadamard gate that we introduced earlier, this one right here, and this is the one that changes between the Z and X bases. So this, now we see our first 2 qubit gate, and there's actually a result that to do any type of quantum computation, you only need 1 2 qubit entangling gate, and then all other 2 qubit entangling gates, if you have enough 1 qubit entangling gates, you can do all of them. And in fact, then you can do any multi-qubit entangling gate. So you could build a valid quantum computer that only has single qubit gates and 1 CNOT gate, for example. This is the most well-studied one, and then you can do any computation on a quantum computer for qubits. So the matrix of the CNOT gate is this thing on the top right. So this is this one is if you, depending on how you order your bits, but don't worry about that. But basically what this is, CNOT stands for controlled NOT gate. So the X gate is also called the NOT gate because if you think of 0 as false and 1 as true, then if this is false, do nothing to the target. This is called the control, and this is called the target. And if the control is ket 0, so it's false, it did nothing, And then if the control is ket 1, so if it's true, yes, do something to the target. And the specific thing due to the target is the NOT gate or the X gate, which is why it's called a controlled NOT gate. And you can also do many other controlled other operations gates in quantum computers. And it's really important because all your multi-qubit quantum circuits are built out of these smaller operations. That's how they're implemented on these hardwares. For gate-based quantum computers, which is the most dominant type of quantum computation model. So specifically, if you have two happy cats, so two ket 0 states, two qubits, both in ket 0 state, and then you apply a Hadamard gate to one of them, and then you apply a C0 gate right after to entangle the two of them. Then what you get is this really special state called a Bell state. It's called a Bell state because after the Bell experiment. So this is actually what won the Nobel, not this experiment specifically, but the Nobel Prize in Physics this year was one for advancements in quantum information, including the C and CHSH inequality, which was one of the experiments right after this Bell test experiment that confirmed the existence of quantum mechanics. So that's really cool. You guys should check it out. So anyway, this Bell here is the equal superposition of ket 0, 0 and ket 1, 1. So this is either both the cats are happy or both the cats are not happy. But you can't have, if you have a Bell state, you can never observe one of the cats happy and the other cat is not happy. So this is entangled because the state of one of the cats definitely depends on the other cat. In fact, it's in this case exactly equal to the state of the other cat. Einstein called it spooky actions at a distance. So this stuff is, I guess, not that intuitive to us, but it's called at a distance because maybe your cats could be really far, this quantum states could be really far from each other and could still be entangled. So this entanglement is something that could be preserved, but it's very delicate, which is why quantum computers are so noisy. So Diego asked a question in chat that's really relevant. The question from Diego is, does quantum gates are basically matrices applied to quantum states which are represented as vectors? Yes, I think, to me, the answer is yes. So in a gate-based quantum computer, that's exactly what quantum gates are. So although it's easy to read off a quantum circuit, but to actually reason about them it cannot just be any matrix and it cannot be any vector. Specifically has to be an unitary matrices and complex valued. You have to preserve the probabilities because we live in a world where probabilities have to always, everything you observe has to add up to 1. So the answer is yes, but not all matrix multiplication is a quantum computation. Like exactly. Yeah, most of the quantum computers on this slide are gate-based. Actually, all of them are. So some of these are software providers. So basically, there's lots of companies that are working on quantum computers, and there's lots of frameworks. This is not at all exhaustive, but I highly recommend checking out the Quantum Open Source Foundation's website if you want to see a listing of all the different types of frameworks. So there's even many types of quantum software and tools that are open source. So anyone, it's free to download. You can get started. People have worked on a lot of educational and learning materials or tutorials for these, including us. That's very comprehensive. And it's very promising because it's easy for anyone to get started. Also, I forgot to mention, this is really important. A lot of the quantum hardware, so although it can be physically thousands of miles from you, but you can run it on the cloud. So that's, anyone can make an account with some of these companies here, just on their online websites. And then you can run any quantum circuit and send it to some hardware really far away. Even if you don't spend any money on this, you could still run quite a bit on quantum computers on real quantum computers, present-day devices, without spending too much money. So, and there's also simulators as well, which may be a much better option for hackathons, for hackathons in with a short time period. This is just screenshots of what, if you run your quantum circuits online, what it might look like. So on the left, this is just a larger circuit diagram, and this is a little problem that that's really interesting that Alberto worked on, which is finding repeated numbers in a vector. So this is just an array. It has, you see that the number 3 is repeated, and so you can run this circuit on the left. And this quantum computer, what it's going to look like is, because in practice there's a lot of noise, so it's not just very clean. It's not exact computation, and so, but you can see that there's a really high probability of the correct answers. So it's you can see which are the repeated numbers, and then the correct answer, it shows up with high probability, and then all the wrong answers still have some noise, but with low probability. Some applications would be that you can do with quantum algorithms could be like quantum machine learning. So this is image recognition. So we're recognizing that this is the number 3. And that's weird. I think I had more slides about the applications. But actually, it's probably best not to hear about the applications for me, given their time. I think you should definitely just look at all the other workshops at this hackathon. There's a lot of workshops on the applications, and there's a good range. And so right after this would be from Wenson on quantum games. And in the last 10 minutes of the workshop, I think it'd be good to just go over getting started with how to use a quantum computer. So there's also a lot of support. There should be support throughout the hackathon if you need support to get started with this, with quantum computing, even if you're new to it, no worries. That's what we're here for. And we'll have mentors, and if none of the mentors happen to have expertise in what you're specifically asking, we'll hunt down for mentors which do. So going back to our quantum entanglement, I'll just show one toy example, but I'll come back and forth to it. So first I will show just this interface online. So this is IBM Quantum Composer, which anyone can make an account for free. Just sign up with your email, and it's really easy to get started. And this is a drag and drop interface. So I'll delete what I have here first. Here I just have 2 qubits. Let me actually change it to be lighter screen. Okay. So here I have 2 qubits, Q0 and Q1. And this is a classical output bit. So where your measurements go into here. So with IBM Quantum Composer, by default, the qubits are in the ket 0 state. But if you wanted to be explicit, you could also put this here. And first, I'll just do a measurement on one of them. Yeah, you can also, if you measure or not, this just shows you what the state is. And so right now, both qubits are in the 0 state. So we haven't done any gates to them at all yet. But if you do we can build a Bell state. So you drag this Hadamard gate. The first thing I'll notice is that here now this top qubit is now equal probability of being both 0 and 1. So reading from top to bottom is reading from left to right. So this, right to left, sorry. So this right bit here could be 0 or 1, but this left bit is still definitely 0 and not 1. We haven't touched this bottom qubit yet. And if you then put a CNOT gate here, then this gives you equal probability of both 0s and 1s. And you can also see this on, this is the Q sphere. So it's basically, it is a block sphere. It just also includes color, which could be helpful. So this color will tell you the specific complex number. So just because we're visualizing real numbers, but there's also a complex number here, which doesn't affect, which many times you won't need to visualize the complex numbers, but in case you want to know them, here they are. And so you can see here, you scroll over it, it tells you a bit about the probability being half. Although in this case, I don't know why there's exactly 1 at the end. So there's many other operations you can play around with, and you can also define your own. So this is drag and drop, and it's a good way to get started and also see what, just try some small circuits and get some intuition for these quantum states and circuits and measurement. But what I'd really like to point you towards is this right-hand side. So this right-hand side here says Open QASM 2.0, but you can also play around with it also here. So this basically gives the code version of what you wrote on the left-hand side. For the hackathon, you probably will be actually mostly writing this code, but at any point you can always visualize the circuit that you have. This is just with Qiskit, but they're just as easy out-of-the-box demo, but you can use any choice of platform in this hackathon. In fact, any combination of platforms. And if there's some integration between these platforms that hasn't been built before, that's just, you can go ahead and build it. That's actually be really cool to bridge more of these different software tools. So on the right-hand side here of the screen, you can see that this is the code. This code exactly tells you what is happening on this left-hand side. So this is a quantum register, and this is a classical register. And you set both qubits to 0. You do an H gate on the first qubit, and then you do a C0 gate. So the code, you can code in terms of just these quantum gates. You could also want to write in higher level code. So this Open QASM is quantum assembly language. It's a specification. And this is just exactly what are the gates you're applying. But with higher level programming languages, so this is Qiskit, here you can import, this is a framework that's just built on top of Python. So you can import anything from Python, and it also can work well with other packages that are out there. So, you can click here, Open in Quantum Lab. So when you make a new account, you can see Composer and Lab. And so Composer is this drag and drop interface, but Open in Quantum Lab will take you to this, well, it will load a little bit, but it'll take you to this online in-browser Jupyter Notebook interface. So there's a few that you can have in the launcher, just like what to get started with. So you could start, you can learn about Python and Qiskit, and there's a lot of code tutorials. There's also a whole GitHub repo of all these tutorials. There's also a whole free textbook. So all of these are good resources, and there's also recorded lectures online from past Qiskit courses in summer school that are really good. As a demo, I downloaded this Deutsch Jose one, so I have this open in a different window, but I can just show you what it can look like if you run these. So in an in-browser, this is just a tutorial demo that comes with the link to this. I'll put in chat. So this comes from here. Okay, I just sent the link to this tutorial in chat. You don't have to open it now. It's just if you wanted to take a look before or after. So, so this is the specific folder of Deutsch Jose algorithm, and this is a toy quantum algorithm. So it's one that's included in most intro quantum algorithms, intro quantum computing kind of learning materials. So, so you'll notice here, I can just shift enter to run. Oh, well, it says 44 because I already run this, but I can rerunning it basically. And then we can run. These are some recap images. These are just images. They're pretty cool. And you can see here it compares a classical circuit with a quantum circuit. I would say that the quantum circuit looks simpler, or at least I think in a few minutes, it wouldn't take that long to explain the quantum circuit, but I think the classical circuit is a lot more detailed here. So in general, the gate-based quantum computing, what it's called the circuit model, and it just means that you draw a circuit diagram with the states on the left, the gates in the middle, and the measurements on the right. And that's all there is to it. It's a simple recipe. And so you can make random circuits in Qiskit, and so this is random. So if I rerun this again, it'll give you a different random circuit, as you can see. And there's lots of different modules. So final thing I should mention, I think here is that you can have classical gates. You can have a classical simulation of your quantum computation, and that's efficient because it's just running on your classical device. If you're running on quantum hardware, so you may have to wait in a queue for the other people's also wanting to run on the same quantum hardware to run first. But this thing is called a simulator. So you can import, and there's many simulators out there where you can simulate any quantum computation that's small enough. And
Lia, are you there? Creo que ya tuve problemas técnicos, pero bueno, ahorita en unos minutos comenzamos la segunda sesión a la 1 de la tarde con el tema Quantum Game Development at an Introductory Level. Los veo en un momento y bueno, creo que ya nos puede escuchar, pero agradecemos mucho su participación y toda este resumen de lo que es el cómputo cuántico para que puedan comenzar. Nos vemos en la siguiente sala y que tengan buena tarde.